I will calculate the difference between the standard enthalpy of a reaction and the standard internal energy of the reaction using the definition of enthalpy, H equals U plus PV. And here you have the standard enthalpy of the reaction at temperature T. It equals this because of the definition of H. And we separate the two terms to get the standard internal energy of the reaction plus the change of the product of PV of the reaction. And we make our first approximation here. We assume the change of the product of PV of solids and liquids is negligible. Therefore, this delta PV is approximately just this delta PV of gases. Then we make the second approximation in which the gases are treated as ideal gases. Therefore, PV equals nRT. And then we make the third approximation. The reaction temperature remains constant or approximately constant. And we can thus use this equation assuming R and T are roughly constant. Because H and U are state functions, we do not have to ensure the temperature remains constant throughout the entire reaction. We just need to make sure the initial temperature and the final temperature of the reaction are roughly the same. So again, we can use this equation to estimate the difference between the standard enthalpy of the reaction and the standard internal energy of the reaction. Again, the difference is simply just R times the reaction temperature times the change of the number of the moles of gases per mole reaction. And again, there are three approximations. First, the PV change of the solids and liquids is negligible, and the gases behave ideally, and the reaction temperature remains roughly constant. This delta N gases is unitless because the physical meaning of delta N gases is the change of the number of moles of gases per mole reaction. For example, this reaction delta N gases equals 0 minus 1.5, and that's negative 1.5. And it means if we have 1 mole of H2 reacting with half a mole of O2, we produce 1 mole water in the liquid phase. The number of moles of gases changes from 1.5 moles to 0. So there's a negative 1.5 mole change per mole reaction. And delta U, delta H are typically from 10 to 10,000 kilojoule per mole, depending on the nature of the reaction. For combustion reactions, usually we observe several thousand kilojoule per mole internal energy change and enthalpy change. And this number is usually much greater than this RT delta N gases. If R is 8, T is 300, delta N gases is 2, and then the product is roughly 5,000 joule per mole or 5 kilojoule per mole. 5 kilojoule per mole is much smaller than the magnitude of the standard internal energy or the standard enthalpy of a combustion reaction, which is often several thousand kilojoule per mole.